Hi everyone. Our next topic after expectations and expected values is variance. It's the natural follow-on to that topic. So we'll spend a little bit of time defining it. We'll also introduce its nearly synonymous but slightly different relative standard deviation. And we'll use it in some examples, and then we'll look at its properties and see what happens, how independence between random variables influences calculations of variances of sums, and we'll talk about that for a bit. We're going to finish the lecture, though, with a new topic, we're going to introduce different types of generating functions. These are pretty different objects from things that we've seen already, and they're really useful for introducing a new perspective or a change in perspective when trying to solve problems. Sometimes things are really easy to solve with generating functions that are more challenging to solve other ways. There are lots of different types of these things. We're going to eventually talk about two of them, but in this lecture we're going to introduce probability generating functions. All right, let's get started. So expectation, you can sort of describe, which is what we talked about last week. You can sort of say that the expectation value, or just I'll write expectation, which we wrote kind of like this, where capital X is a random variable. This by the way is also called mean. I think I used that term last time. Mean value. This is what this is useful for. Is this tells about what value X will have, or what you expect it to have. And what I mean by emphasizing the word will here is that X is a random variable, and so it can take on lots of different values, and the expectation value, or the expected value, is supposed to be some sort of an indicator of what kind of value you expect it to have among those different values, or near them, or something like that. Remember, it doesn't have to be one of the values that X can take on. The expected value doesn't, at least. But nevertheless, it gives you some sense of what value X might take on among its various options. And so in a similar way, variance has kind of a similar use. So variance, which we'll write as VAR of X. So again, capital X is any random variable here. This is about how much variation we expect in the values that X can, or in the values that X can take on. Or how the variation that X will have. So again, X is a random variable and it can take on various different values. The expectation value gives you some idea of what value you might kind of typically expect to find it near. And the variation, or the variance, tells you kind of how far away you might expect to find yourself from that value. How much does it typically vary from that value where you expect to find it. So I'm going to draw a little picture here to try to illustrate this. So suppose you have some PDF function for the random variable X. And let's just make an arbitrary looking distribution. May as well not make it look totally boring. Maybe it has a couple of humps like this or something. Oops, oh no, I'm gonna draw it again. Like that. So let's say that's the PDF of X. Then the expectation value
might be sort of here. Let's just say I'm going to use a different color. So you might sort of, maybe it would be that the expectation value is around here. And so that just gives you some idea of where you might find the random variable x. And the variance gives you some sense of how far away, or what is the kind of spread. So we'll write this as write this as variance of x. So it tells you something about the width or the kind of spread of the values that you might typically find, where you might typically find the random variable x. So again, I'll put like a little approximate sign next to there, because this is just a very crude sketch. This doesn't really tell you how to calculate it or anything, but it's meant to tell you that the variance is somehow indicative of the size of this lump in the probability density function. And so now we can go ahead and make a proper definition of it. And so we'll do that now. So we're going to just define variance. So let's let x be a random variable. And let's suppose that it has a finite expected value. And we'll name that mu. That's a common symbol to use. Then the variance of x can just be stated as a simple formula. So then the variance of x is the thing that we're going to, or the notation we're going to use, var of x. So I'll highlight this. That's the thing being defined. And so it obeys. It's just given by the formula. The following formula. And it looks like this. So it's the expected value of the squared difference between x and its mean, or x and its expected value. Right? So that's the defining relationship for the variance. So it's the expected value of the squared difference between the random variable and its expected value. There's another way to write this, which is often more useful. So equivalently, so you can consider this part of the definition if you want, but we'll prove it. You can write it as this: variance of x is equal to the expected value of x squared minus the square of its expected value, or the square of its mean. All right, so that's the definition there, and we'll do a little proof to show you that that second version is equivalent to the first. But the first thing I want to do is just make a comment. So notice the following. If you look back at this top definition here, oops, I didn't mean to strike it out, but this guy here, since it's the expected value of a bunch of numbers which are always positive, because this is a squared difference, then the variance itself has to be positive, because it's just the expected value of a positive thing. So notice that the variance of x is always greater than or equal to 0. It's never negative. You can't have a negative variance. And that fits with this kind of picture over here. It's certainly possible to have a negative value for the expectation value. You know, that could have been somewhere over here if you had a different distribution. But it doesn't make any sense, at least in this picture, to have a negative value for the variance if the variance is somehow describing to you how large is this kind of like non-zero region of the distribution. If it somehow quantifies that, it wouldn't make any sense to say the region is negative in size, really. So it's never negative. Okay, and so let's do that little proof that those two things are the same. So we'll make a little proof of equivalence. of the two things in the definition there. So here's the proof of the equivalence. So I'm going to start with the first line and then turn it into the second one. So let's just copy the first one. I'll start from that. Right. And then so we're going to use some of the properties that we introduced in the last lecture. So this quantity here, the expected value, I'm going to expand the argument. And so we get x squared plus mu squared, and then minus 2x mu. Right? And so now I'm going to I'm going to go forward with this, and I'm going to use properties. So use properties 1 and 2 from last lecture, or section 5.2, I think it is, but from the last lecture. So last lecture. Right, and so I'm going to write that this thing here, this is the expected value of x squared plus, now you could write the expected value of mu squared, but mu is a constant, so this is just mu squared, and then minus 2 mu times the expected value of x. So again, this is using properties of the expected value that we showed in the last lecture. Okay, and then remember that the expected value of x, this is mu, and so what we have is the expected value of x squared, and so this term here is going to be minus 2 mu squared, and that's plus mu squared, and so what we're left with is minus mu squared, which if you go back up, that's the thing we were trying to prove. And so that's the end of that proof of the equivalence of those two things. Okay, now let's just try a little bit of an example. So we'll try and compute an expected, or a variance. So we'll do an example for one of the simplest distributions, maybe the simplest distributions. So let's say let x be Bernoulli distributed with parameter of success p, and then the goal is to find the variance of x. Now it turns out that of these two different forms up here, this one is probably more useful, certainly the one I'm about to use. This guy here, it's useful in one way, like for seeing that the variance is always positive, but I think we're going to use the other one probably more often. But so let's go ahead and do this. So from the last lecture, we found the expectation value of x if it's Bernoulli distributed, but we can find that again. It's very easy. So the expected value of x, right, that's a sum, but there's only two different values that x can take on here. It can take on the value of 0 times the probability that it takes on the value of 0, so that's 1 minus p. And then plus it can take on the value of 1, and then times the probability that it takes on that value, which is p. And so this expected value is p. So that's quite simple thing for the Bernoulli distribution. So that's what we're going to call mu. And the expected value of x squared, it works in a similar way. So we write down the value of x squared times the probability of having that value of x squared, and then we sum. So the value of x squared, the first option is 0, or if you want, you can write 0 squared, times the probability of having x equals 0, so that's 1 minus p, and then plus the value 1 squared times the probability of x having the value of 1, and that's p. And so this is again equal to p, right? So the expected value of x squared is also p. And so this tells us then we just plug this into our formula, the variance of x. Right, so that's going to be equal to the expected value of x squared That was a little clumsy there. Minus mu squared, or the square of the expected value. And so this is going to be p minus p squared, or you can write this as p times 1 minus p. Yeah. Sometimes you might write this as p times q, where q is the probability of failure. Some people like to do that. All right, so that's our first little example. You can sort of see, like, what. So let's just put in some values. So, for example, within the example, let's say you had a fair trial. So fair trial, or fair coin. So for fair trials, where p is equal to a half, then what do we have? So the expected value is a half, and the variance, which tells us like sort of how much we expect that to vary by, is a quarter. Oops. Now, it's a sort of a funny description. The Bernoulli distribution is sort of a funny case to start with because it's so simple like that. And of course, you never do find x equal to a half. And it sort of doesn't make a lot of sense. You're never going to see x equals plus or minus a quarter from a half either. But these are just numbers that kind of characterize the area around which you expect to find x, and sort of the size of that area. So where is that, and how big is it? So that's kind of what these things do. Yeah, you could kind of go back to this picture here and think, this guy, I think this is probably a good idea. Expected value here. This answers the question, where? That's what the expected value answers. And the variance answers the question, how big? I don't know, I'm just making this up, but I sort of think that's a useful way to think of these two different things. Okay, so now we'll go on to our next thing. We want to just introduce a new definition here, a common term that's used. I think this is not introduced as a definition in the book, but it probably should be, or in the notes rather. So this is definition of a new term. Let's say you have, if x is a random variable, and it has variance var of x. And let's say it's equal to some quantity that you call sigma squared. And then the quantity sigma, which is the square root of that, of course, is called the standard deviation of x. And this is probably maybe a better description of kind of the size of that non-zero portion of the probability density function, because let's think about this. So what are the units of x? So suppose that x had units of I don't know, meters or something, and then you go up here and you ask yourself, well, what's the units? What are the units of the variance of x? Right. So here's its defining thing. So it's the squared difference between the variable and its mean, and so it's going to have units of meters squared. And so if you go to this kind of picture, this thing here would be kind of, oops, sorry about that. This thing here would be something like meters, and this, if it's actually the variance, would be meters squared. And so probably you might want to say this is like the square root of the variance, or the standard deviation. But nevertheless, if the square of the standard deviation gets bigger, so does well, did I say that right? If the standard deviation gets bigger, so does its square. And so this picture is still kind of fine. But if you want to get your units consistent, you probably should think of this size here as being represented by the standard deviation rather than by the variance. Okay. Now let's sort of introduce some kind of properties of the variance, similar to what we did with the expected value. Just make sort of a list. I think we're just going to show two properties. So variance properties. Right. And yeah, we're just going to show two of them here. So let's say, so the first one, we'll introduce the first one and then prove it. And the second one, we'll prove it in the next chapter. But so we're going to say, let's suppose you have a random variable x for any random variable x. And let's say you have two real numbers, a and b. Then it's the case that the variance of ax plus b is equal to a squared times the variance of x. And we'll go ahead and prove that, but the first thing I want to kind of comment on is, notice this equation is kind of funny. There's no b on the right hand side, right? And that makes sense if you think about what's happening here. So this is saying, what is the variance of a random variable that's been linearly transformed like this? So it's been scaled by a, and then you add b to it. And so if you go back up here and think about this picture again, if you change the random variable to some other one, and let's say you forget about the scaling by a part, if you just shifted it by some constant, this whole curve here would just be like sort of shifted either to the right or to the left. And so it's not going to, shifting that curve to the right or to the left isn't going to influence the description of the size of its kind of non-zero region. So it sort of makes sense that there won't be any dependence on the parameter b when you look at the variance of the transformed variable. And so let's just go ahead and do a proof of this. It's pretty straightforward. You just put in the left side and hammer away at it until it looks like the right side. So we'll write the variance of ax plus b. All right, and now we're going to put in the definition of this. So it's the expected value of ax plus b squared minus the square of the expected value of ax plus b. Right? And now we just expand these two guys. So the guy on the left becomes the expected value of a squared x squared plus b squared plus 2abx, right? And then minus the square of a times the expected value of x plus b. Right, so that's just evaluating the expected value inside of there. All right, and now again we use our rules that we saw last time, and so this thing becomes the expected value. Sorry, let me move this. I'm going to move everything a little bit to the left. I'm going to get it a little, maybe slightly crowded here. Oops. There we go. Okay, and so we're going to get a squared times the expected value of x squared plus the expected value of b squared is just b squared plus the expected value of 2ab, so that's 2ab expected value of x, right? And then minus the square of this thing in square brackets, and so that's going to be a squared expected value of x squared minus b squared, and then minus 2ab expected value of x. Yeah. And now if you look at this, there's a lot of things that kind of cancel out, so I'm going to use a different color here. So let's see, here we have the cross term 2ab expected value of x, with a plus sign in front of it, and then here we have minus that. So those two are going to cancel out. We've got a b squared here, and here we've got a minus b squared. And so the only two terms that are going to survive to the next line are this one and this one. So we'll write those out. And so we get, oops. So we get a, and they both are multiplied by a squared. So we get a squared times expected value of x squared minus the square of the expected value of x. Right? And if you think about that, so what is this quantity in square brackets here? Right? Isn't that the variance of x? And so that's what we were trying to prove. So we get a squared times the variance of x. And so that's our little proof of this property. All right. The second property that I'm going to introduce, this is very similar to the last lecture. So this property, it's almost dangerous writing this property out because it's a specialized. It's not true. So this property I just showed here, this is true all the time for any random. I mean, the next thing I'm going to say is also true all the time, but it's got like a caveat to it. Whereas this, it doesn't. It's just any random variable. If you transform it, then this tells you how to transform its variance. Now I'm going to introduce the second property, which is a little more specialized, and it says, so we'll say, let's say you have two random variables, x and y, and they're independent of each other. Right, and we haven't really explained too much about what this means. I think you've seen independent in terms of probability, but we'll get back to this. So so what's important here is, what I want to emphasize is that these have to be independent of each other in order for the following thing to be true. And I really can't emphasize that enough, because I don't want you to be looking back at your notes and seeing this equation, maybe when you're under duress and trying to answer some exam problem or something like that, and you see this equation, you're like, that looks like a great equation, I'm just going to take that. You could get yourself into trouble if you did that. But so if this is true, then the following is true, that the variance of x plus y is equal to the variance of x plus the variance of y. But in general, this is not true, that the variance of x plus y is the variance of x plus the variance of y. This is only true when x and y are independent of each other. So I want to emphasize that. Okay, and then you can extend this, so, and then by extension, let's say you have a whole bunch of random variables. So you have all these random variables that I'll call x sub I, and they're all independent. Then let's underline that independent again to kind of remind you that this is important. Then by extension, you have the same kind of expression. So we have the variance. Oh, and let's say I equals 1, 2, and so on, up to n. Yeah, that's what I'm going to use. Move this down a little bit. Then the variance of the sum is going to be the sum of the variances. But again, you should be putting stars all over the place around here to remind yourself, don't steal this equation, don't steal that equation. Make sure these are only for independent random variables if you're going to steal that. Okay, and so we'll see the proof of this later. So proof in chapter 5 of the notes. That's when we'll start talking about well, you'll see what we start talking about in chapter 5. I don't want to spoil it. All right, and so now we move on to our last topic of this chapter. We're going to sort of start it today, and we'll finish it in the next lecture. These are two different things that we're going to introduce here. Both of them are a form of something called a generating function, which I think you've seen before in some context, but you don't have to know anything about them from there to talk about them here. So we're going to talk about two types of generating functions. One of them is called a probability generating function. Which you can write with the acronym PGF. And the other one, I'm going to copy this since it's such a long thing to write. The other one is called oops. So much for saving time. The other one is called a moment generating function. And that's MGF. And so we'll introduce both of these, but I think today we're only going to introduce the PGF. Right, so this is our final sort of big section of chapter 4. All right. Now, before I get in, again, as usual, before I do anything kind of formal, I want to talk a little bit about what this is sort of about. What are we doing this for? What's going on here? So when someone tells you about a new random variable, you can kind of characterize it with a bunch of different things. So far, a random variable x was kind of described or characterized by the following things. So the probability mass function, if it was discrete, or the probability density function if it was continuous. And I think we always called that f of x. The cumulative distribution function, it's another thing we use to kind of characterize the random variable. Or the inverse of that. The inverse cumulative distribution function. We also talked about the expected value and the variance. You can take these as defined. Like that. So all these are different ways that we could kind of tell you sort of what's up with this random variable. What does it do? What kind of properties does it have? These are all things that we could introduce. And the generating functions that we're going to introduce are just sort of similar in that they're useful for describing the random variables. How they describe them is a little more opaque, I think, but they're still useful. So these three things so far, they had a very kind of intuitive description of what they were. The next things we're going to introduce, these two generating functions, the probability generating function and the moment generating function. These have different applications, really. These offer an alternative perspective. So just sort of another way to look at the random variable, or another thing to think about that's related to the random variable. But it really is the case that it's sort of opaque in that we're going to define these things, and they're relatively simple to define. But you'll look at the definition and think, well, what the hell is that useful for? And it may not be clear right away, but we'll try to show you how they're handy. So it's similar. What we're doing is very similar to, I'm not sure what your experiences are so far, other areas of math and so on, but what this is similar to is, suppose you had some function, so this is similar constructs. Or things with similar purpose. like if you have a function, and then maybe you want to, don't think about the function by itself, think of it as a what is the Taylor series of the function? Sometimes that's useful. I don't know, depending on whatever you're doing with the function, sometimes it's handier not to write the function so explicitly, but to instead like sort of go into this other space where you look at it as a series, as a representation, a Taylor series. So that's a common thing that you do. Like this is a handy trick, for example, when you want to solve differential equations. Sometimes it's better to replace the function with its Taylor series, and then suddenly the differential equation becomes very easy to solve. Again, I don't know if you've run into this yet in your math existence, but you will at some point, so it's kind of useful to see this. Another example is like, let's say you have some function on one side, and you transform it using a famous transform called the Fourier transform. So this is, again, you may never have heard of this, I don't know, but I just thought I would point out to you what's going on here. You have something that you know what it is and how to deal with it. Sometimes it's useful to kind of put it through some machine and turn it into something else, and so this is the Fourier transform of the function. This is useful in physical processes for if you have something that's like a function of time, let's say over here, and then you perform this transformation and it gives you another thing over here that's a function of frequency, which is inverse time. So that's sometimes handy. Just like, it's sort of like, you ever get stuck on a problem and you're like, I don't know what to do here. And you just start trying different things. Like, oh, what if I just square everything? What if I just add these two equations that I have? Maybe something useful will happen. Sort of like that. If you change perspective, sometimes problems that were really difficult to crack suddenly become straightforward. And so this is kind of like the utility of these things. Another example is a function. And I'll just stop with this one because I don't really know if you've heard of any, or I think you've heard of the Taylor series, I hope. The Laplace transform. And then these backwards arrows are like the inverse of these transformations. These are 3 examples of different perspectives that are used sometimes to try to make your lives easier. Maybe you haven't encountered these 2 yet, but you will see that they sometimes are helpful for doing things. And I think it's important to think, because what happens with these things that we're about to introduce, the probability generating function and the moment generating function, it is really the case that when you first look at them, it's like, okay, fine, that's very simple, because it is really a simple object. They're both simple objects. But like, well, why are you telling me about this? Are you just trying to make difficult homework problems for me to solve? What the hell is this for? And really, this is what it's for, getting a different perspective to try to improve your ability to solve problems. Okay, and so what are these really explicitly useful for? So there's a small list in the notes, or something like this. So the probability generating function and moment generating functions, these are useful for the following. I mean, there's other reasons they're useful, but there's just a handful of things. We know we're about to tell you something weird, and so we want to try to convince you that it's useful for something. So it's often useful for proofs. Sometimes it's easier to prove things using generating functions than it is using the functions themselves. It's useful for recognizing or identifying distributions. For random variables. Maybe you have some random variable, you don't really know what it is, and then you do something to it and you realize, oh hey, that's Bernoulli distributed. It's that kind of thing. Or sums of random variables. It's kind of redundant, but the reason you'll see why sums are kind of introduced here. It's also useful for finding moments. I don't know if we've named these things moments, but I'll write this as the expected value of like x to some power k, where k is equal to 1, 2, and so on. So these are called moments. So we've sort of seen these, like we've seen the expected value, the mean is the expected value when k is equal to 1. The variance is related to the moment when k is equal to 2. Anyway, so it's useful for these things that we're about to introduce are useful in these contexts, and we'll see that. But I just want to convince you that, or I want to motivate that there is some purpose to what we're about to do. Because when you first see this, it often feels like there isn't. So, all right. So we're going to introduce the first one that we'll talk about today is the probability generating function. So probability generating functions. Or PGFs. These ones are really for discrete random variables. And what they are is a power series representation. So this is a power series representation of discrete random variables. I should point out that these little examples I gave up here, the Fourier transform and the Laplace transform and so on, those are not actually so... Sometimes that is a direct connection to these things I'm about to introduce. But that's just for your future lives, for enjoying some beauty. You'll see those things later. Okay, anyways, so let's talk about power series representation for discrete random variables that we call the probability generating function. Right, so we're going to go straight into the definition. So how do you define this thing? So the definition of a probability generating function is as follows. So suppose you have a discrete random variable x, and it isn't really just any one, it has to take on certain values. Uh, 0, 1, 2, 3, and so on. You could kind of remap a discrete random variable so that it takes on those things, and maybe you can use this all the time for any discrete random variable. At least you can imagine trying to do that. And let's say that it has a PMF and so on. With PMF f of x. And I just want to remind you what that actually is. So that's the probability that x is equal to little x, that x takes on value little x, and so these are the different these things here, the different values that little x can have. Okay, then the definition. The PGF for x or of x. Oops. PGF for x, and we'll highlight this because this is what we're defining, is, and first I'll tell you the notation. It has this funny notation, is capital G with a little line on the side, subscript of capital X, and then it has an argument usually called s, lowercase s, where, and then we'll define it with an equation. Following equation. So it's the sum as little x goes from 0 up to infinity of s to the little x to the power of little x times f of x, the PGF, or sorry, the PDF, the PMF for x. So that's the definition right there. And if you look at that for a little while and ask yourself, what does this right-hand side look like? So here's a quantity, some function of x, and then here's the probability that big X takes on the value little x. And so if you think about what this is the expected value of little s raised to the power of capital X. So that's the same thing, right? It's the expected value of this function of capital X evaluated at little x. So here's the value times the probability that little x takes on that value, and then here's the sum over all the possible values. And so that's why that's the expectation value of little s to the x. All right, so we'll just do a little calculation here of one. We'll try to compute the probability generating function. So I have to be careful. You might slip up and just call things generating functions, and then it gets confusing what you're actually talking about. So let's do an example. All right, so let's suppose that we have a Poisson distributed random variable with parameter lambda. And so again, this takes on values as we want. 0, 1, 2, and so on. And it has to have a very specific PMF for this. So it takes these values and it has PMF. F of x is equal to lambda to the x e to the minus lambda divided by x factorial. And again, this is for little x is equal to 0, 1, 2, and so on. So that's just the definition of the Poisson distributed, or the Poisson distribution. And so, okay, so our goal is to find the probability generating function for x. And I'll tell you we'll see this in the next lecture, but the reason we want to do this is that there's a unique probability generating function that goes along with any distribution. So in this case, there's one probability generating function that goes along with the Poisson distribution, and we're going to find out what it is. So that's the purpose. We'll see that. We'll start the next lecture talking about the fact that is the case, the sort of uniqueness of this. But okay, so this is what we want to do. So let's just look at the definition. So the generating function, the probability generating function is the following. So it's the sum as little x equals 0 to infinity. Right, and then we write little s to the power little x, and then we write the probability mass function evaluated at x. And so we have lambda to the x e to the minus lambda all divided by x factorial. Right? Now, we can kind of tidy this up a little bit, right? This guy here doesn't do anything in the sum. It doesn't change as x varies, right? As the index of the sum is x. So this guy's just a constant, so we can pull that one out. So I'm going to do that. So e to the minus lambda. And then I'm going to relook at the sum, x equals 0 to infinity. And what I have here is s times lambda to the power x divided by x factorial. Now, if you stare at that for a while and ask yourself, what is it that you're actually seeing here? I want to point out to you this thing here. This is the Taylor series. For an exponential e to the s lambda. Right? So that's what that quantity is. I should probably change the color of that, but well, it's a little too late. So yeah, I'll go ahead and do that. So this is the Taylor series. Of the exponential e to the s lambda. And so I'm just going to make use of that. Right? So I got e to the minus lambda times e to the s lambda. Or in other words, this is e to the lambda s minus 1. And that's the answer. So, this is how it goes when you first see these things. So someone says, go ahead and calculate it. So you've calculated it. What does this tell you? I don't know. I don't know. But it tells you what the probability generating function is for the Poisson distribution. And sometimes if you're doing something with a variable that has a Poisson distribution and you're like, you know what, I'm tired of this. I want to start looking at everything as a probability generating function. You start switching everything up. And then every place where you had your variable, you now use its probability generating function, or that kind of thing. So that's what this is used for. Okay, now, or maybe, you know, this is what we'll see kind of tomorrow or in the next lectures. You find the generating function for something, you see it has that form, you say, haha, oh, that must mean this variable is Poisson distributed. So that's the kind of utility that this has. All right, we're going to finish today with a sort of a claim and a proof. So we'll make a claim. Claim the following. If x is a discrete random variable, taking on values, the usual here, starting at 0, 0, 1, 2, and so on, with probability mass function f of x, and with probability generating function g sub x of s, then the following is true. And the following thing that's true is handy, and then we'll go ahead and prove it. So it's the probability that x is equal to k. This is going to be equal to 1 over k factorial times, and I'm going to write this in a sort of a long way, and then I'll make a shorthand notation for it. This is the kth derivative with respect to s of the generating function, the probability generating function, evaluated at little s equals 0. Right, and so that's just, I'm going to use a shorthand notation for that. So I'm going to define that to be 1 over k factorial. Maybe you're used to this notation, maybe not. And we'll put in parentheses up here k to represent the kth derivative. And then we'll write evaluated at 0. So that's just a shorthand notation for the thing on the left-hand side, for that thing in the middle here. Okay, so now let's see if we can prove it, and then that'll be the last thing we do in this lecture. All right, so we'll make a proof. I think this is kind of a wishy-washy proof, I think. So I'll put sorta, because it's going to be kind of like, we're going to kind of motivate it exactly. It's not I wouldn't say it's totally proved, but I think you'll be happy with it. So okay, let's look at this proof. So let's say we just try to look at the generating function by itself, right? So this is the definition of it, right? So what I'm trying to do is I'm just going to look at all these things and see what they look like, and then I'm going to evaluate, so as functions of s. So take all the derivatives and then evaluate them at 0 and see if they look kind of like what I'm claiming. Okay, so this is the definition of the generating function. We go from x equals 0 up to infinity, and then we have s to the x and f of x. Right, so that's just that guy. Let's look at the next one. The first derivative of that, evaluated at s. So that's a sum. X equals 0 to infinity. So the derivative doesn't do anything to the probability mass function, right? It's a derivative with respect to s. So it does something to the s to the x. And so what we get is x times s to the x minus 1 f of x. Right? So that's just evaluating doing one derivative on that thing. All right, now let's look at the second derivative, and then we'll generalize. Right, so the second derivative might need a little more room here. So again, it's the sum. And, I'll just take the derivative of the line above. And so x doesn't do anything. This is derivative with respect to s, remember? So go back up here. All these derivatives are with respect to s. Maybe I should make that s a little more obvious. It's kind of like that. There we go. Okay, so the derivative with respect to s of the line above is x times x minus 1 s to the x minus 2. Like that. Right, so that's this guy. And then the generalization, you can kind of see what's happening, I think. Maybe, I hope. Hope you will believe me that the kth derivative then looks like this. Again, I got kind of crowded. Let me put this down a little. So it's going to be a sum, x equals 0 to infinity. And then we have a whole bunch of different things that would be multiplying each other here, right? So we'd have x times x minus 1 times x minus 2 dot 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 times x minus k plus 1. Right, so that's what would go here. And you can check, does that make sense? Right, so there's x, and here we stopped at x minus 1 because k is 2. And so x minus 2 plus 1 is x minus 1. And so yeah, so that fits. That's this thing with k equals 2. Okay, and then we're going to multiply this by s to the x minus k times f of x. Oops, that's getting kind of smushed. Yeah, so that's the generalization. All right, now, so to do this proof, the next thing I'm going to do is I'm just going to take each one of those 4 lines. So this, the reason I say this is sort of a proof is that I just made this leap, and I hope you believe me. And the next thing I'm going to do is I'm going to just evaluate each of these. Each line at s equals 0, right? Because that's what, if you go back up here, that's what we're claiming, that if I do that, if I evaluate that thing at s equals 0, what I'll get then is this probability that x is equal to k multiplied by this thing flipped over, so k factorial times that probability. So let's see if that's true. So that's the proof. All right, and so so now I'm going to really take advantage of my note-taking thing here. I'm going to just copy this whole thing. And then I'm going to go through and sort of put all the s's to 0 and see what I get. Right, so I've got that there. All right, so the first one, make the s 0. Right, and so here I've got this guy as 0. And I need to remember here, so I should put like a line here. We're gonna get to this stuff here. It's all true. I want to evaluate s equals 0. I want to remind you. So what is 0 to the x, right? So that's almost always 0, except when x is equal to 0. Otherwise, it's 0. So in this sum here, right, I've got 0 to the x. So only one term is going to survive this sum. It's the term where little x is actually equal to 0. And so this guy becomes just 1 times, so that's 0 to the x, right? F at 0. And what is f at 0, right? Isn't that's the probability that x is equal to 0, right? And so that's checking the very first line. So let's go back up to this thing that we're trying to prove, right? So there I've got probability that x is equal to, in this case, 0. That should be 1 over 0 factorial, which is 1. The 0th derivative, so the function itself, evaluated at 0. And that worked. Right, so that checked. Now let's fix all these other guys. I'm gonna work through here. So this guy's 0. There's kind of a cheap trick that I'm erasing. Do all this stuff by erasure. That always bugged me when teachers did that on the board. Because you can't do it so easily on paper. But maybe you're not using paper either. Okay, so what is this again? So we look at this sum, right? We've got this sum here. All these terms are going to be made to vanish by this factor here, except when little x is equal to 1, right? That's the only thing that's going to cause this to be anything other than 0. And so this is just then f evaluated at 1, which is the same thing as the probability that x is equal to 1, right? And that checks as well, because 1 factorial is 1, right? So now let's get through this second to last guy. All right, so this guy is 0, and this guy is 0, and so on. And you should see the pattern here, right? So look at this sum. All the terms are going to be made to vanish by this guy, except when x is equal to 2. And so we're left with this guy when x is equal to 2. And so when x is equal to 2, what we have is 2 times 2 minus 1 times f of 2. And of course, this is just 2, but it's 2 factorial, right? And so this thing is equal to the probability, or I should write it, sorry. It's equal to 2 factorial times the probability that x is equal to 2. And that's what we wanted. Okay, and now lastly, we'll do the last line here. So evaluate this thing at 0. And again, this thing is evaluated at s equals 0. And everything is going to be made to vanish because of this term here, except when x is equal to k. And so that's then equal to, the only term that survives is x equals k. And so that thing in square brackets then is k factorial. I'll let you kind of see that, let you kind of work on that to see that, times 0 to the 0, which is 1, and then times f of k, right, which is equal to k factorial, the probability that x is equal to k. And that's the proof, sorta.
Okay, so I hope everybody enjoyed that. Variance and standard deviation are probably quantities that you had some notion of or familiarity with even before, whereas the generating functions might be pretty new to you. And I think that you'll find them to be pretty useful as you go forward. They sometimes seem a little abstract at first and strange, but they really are handy for changing your point of view when working on various different things. All right, until next time.